Hello everyone. This video describes volume estimation of trees and forests, which is also a part of the course unit Forest Mensuration and Inventory, Department of Forestry and Environment Science, University of Sri Jayewardenepura, Sri Lanka. Now, when it comes to the tree volume, we talk about the stem volume, main stem volume of the trees. When you look at the picture, you can see the stem is very much irregular. When you compare with a cylinder, cylinder always a regular, geometrically regular shape. The bottom diameter, middle diameter and top diameter, all the diameters are equal. Therefore, it is very easy to estimate the volume by using this equation 5d squared h over 4. But when it comes to the volume, because of its irregular shape, this has become the most difficult parameter to accurately estimate in forestry. Therefore, as an approximation, if you want a sort of a rough volume, we assume the volume of the tree stem as a half of a cylinder, and then we estimate the cylinder volume using the base diameter, the height of the log, and then we divide it by 2. So, the assumption is volume of a tree stem is half of the volume of a cylinder. Before getting into the volume estimation, I want you to learn two other parameters which are strongly connected with the volume. One is the form or the shape of the stem, the other one is taper, which is also, I will describe it later on, but which is also connected to the shape of the stem. The form is the shape of the stem, which is a very much a qualitative guess or qualitative decision that you can make. Therefore, there is a way of quantifying the shape of the tree with a basic assumption that the ratio of the stem or the log volume. Before getting into the volume estimation, I like you to learn two other parameters which are strongly connected with volume. One is form, which is also known as the shape of the tree stem. The other one is taper, which is also linked with the shape of the tree. Now, form is a qualitative guess or the visual guess that anybody can make just looking at the stem, which is very difficult to recognize for some other people. Therefore, in order to quantify the tree shape, an equation has been built which is called the form factor, which is a quantitative figure. Form factor is the ratio of the stem or the log volume to the volume of a cylinder which has the same area at the base and also the same height. Now, when you look at the diagram, the inner part, this part is the tree stem or the log stem, and you estimate that volume, and also you have a hypothetical cylinder which has the same area at the bottom and also same height to the log, and then you divide the stem volume by the log volume. So, other way around, you divide the log volume by the stem volume. How we estimate the form factor? To estimate form factor, we need three measurements or three values of the log, and when I talk about a log, its shape is something like this. Always we call the logs when the top has been removed from the tree. Therefore, we have a diameter at the bottom, we have a diameter at the top. If you look at the most tallest place of a tree, tallest point of a tree, it does not have a diameter. We usually call a log to a piece of stem which has an upper end diameter also. Now, the three parameters you need to identify, you need to calculate or you need to estimate to quantify the form, which is a form factor, is a volume, cross-sectional area and the height of the stem. Volume you have to estimate for the log by different methods which we will be talking about. Cross-sectional area is the area of a certain place of the tree, and this is the top view of the stem when you cut it, and the area of that part is called cross-sectional area, or the familiar term for you is basal area. And the height, if it is a total height, this is the height. If it is a log height, which is cut somewhere here, that could be a different height. Now, these are the 4 common equations we use in forestry to estimate the form factor. There are 4 types: absolute form factor, artificial form factor, Pressler's form factor, and the field form factor. When you look at all 3 equations, all the measurements are similar: volume, cross-sectional area, and height, but they have their own slight differences. Vt is the total volume of the tree with the bar. Now, if you look at a stem again, if this is the tree, total volume is the volume of the stem from the ground or from the base to the highest growing point. This is what we call the total volume. Merchantable volume is the volume of the tree with the commercially available timber. Of course, at the top part you do not have any commercially valuable timber, therefore, it could be somewhere here. So, beyond that point there is no commercial value. Below this point to the ground there is a commercial value that you can sell for the commercial purposes. Therefore, we call it a merchantable volume. And then you need the total height and the cross-sectional area. Cross-sectional area, GL, means ground level at this point. Cross-sectional area at breast height, GBH. Breast height, you know that it is 1.3 meters above the ground level and 90% from the top. So, there are 3 different basal areas. Absolute form factor has total volume, basal area at ground level and total height. Artificial form factor, total volume again, cross-sectional area or the basal area at the breast height and the total height. Pressler's form factor, the difference is the cross-sectional area, which is at the 90% from the top, and the field form factor, volume is different. This time we estimate the merchantable volume, basal area at the breast height and total height. The factors affecting form factor, variables in given equations: volume, basal area and height. Species and genotype, we know that different species are different from the shape and the growth rate and many other parameters, like mahogany is different from teak, teak is different from eucalyptus, different from hora, bulu, all these species. And also within species it depends on genotype as well, because different clones, different genotypes push the trees into different growth rate levels. Therefore, genotype also decides within the species the shape of the stem and the age. I will make a graph to understand what happens with the age. Say this is age and this is growth. At the beginning, when a tree starts growing from the seed or seedling, it has quite a slow growth which becomes vigorous. When it passes the young stage, it becomes much more slower. And the fast growing area, tree try to grow really fast and therefore the shape is different. When it comes to mature, trees are growing more horizontally sometimes than more vertical direction. In that case, the form of this area, the trees of old ages are different from the form of the or the form factor of the trees of young age, which is different from immature age. The stocking or the tree density, we get as an example, we will get two situations, one high density, the other one is low density. For example, same age 15 years. The first case we have high density 400 trees per hectare, second case we have 150. Same species, same age, but same location as well, but the densities are different. One is 400 high density, the other one is 150 which is low density. Now what happens to the competition? Due to the high density, the trees compete heavily for the available nutrients on the soil, water and also the air in the atmosphere. Therefore, there is a high competition with the high density plantations or forest. With the low density 150 trees, plenty of space around, therefore, they have lot of opportunities to absorb water and nutrients from soil without competing with each other. At the same time, in the canopy area, there is low competition because canopies do not overlap. Therefore, you have a low density, low competition, therefore, the growth rate is different. Now, what happens to the growth when the competition is high? Trees try to grow taller to get more nutrients. They use the roots, but to get more sunlight for the photosynthesis, they have to compete heavily and grow fast as possible in height to reach the maximum amount of sunlight. But in low density forest with low competition rates, that problem does not occur. Therefore, they do not bother to go that much taller, but they try to go more horizontally, and therefore, same age, same site, same species, high density, we have taller thin trees. Low density forest, we have thick or the fat trees in the area. Therefore, if you look at a fat tree or a thick tree, it looks more conical. High density, they are thin but tall, therefore, they look more cylindrical. Therefore, the stocking or the tree density also heavily decides the competition, and that decides the form factor. Crown size, again, larger crowns, high rate of photosynthesis, because when the crown is larger, the number of leaves in the crown is also very high. That helps to have more photosynthesis because they can absorb more sunlight, more surface area, more number of leaves. In that case, higher growth rate but more horizontal. If it is very low, the crown size is very narrow, small, the photosynthesis becomes low because of the low number of leaves, low surface area. Therefore, they try to grow again taller. This is with narrow crowns. This is with wide or large crown. These are the differences, and also the site quality. Some sites support better growth rate for the same species, different sites will be very much bad due to different soil types, different elevations and the nutrient contents available. Good sites, lot of nutrients available, lot of sunlight, therefore, more opportunity to do photosynthesis and heavy growth. Again, the trees are more conical, what we call good site. Poor sites, low amount of nutrients, therefore, trees cannot grow horizontally fast, therefore, they try to grow much taller. These are the factors which decides the form factor in forestry. And the relationship between the shape and the form factor, I told you earlier, form factor is the ratio of the log volume to the cylinder volume, which has the same area at the base and same height. Now, if the form factor is 1, it is the cylinder divided by a cylinder. Therefore, the shape is cylindrical. 3 by 5, which is cubic paraboloid. Cubic paraboloid, the shape is like a barrel, something like that. Quadratic paraboloid, which is very common assumption in forestry, form factor is 0.5, half is 0.5. Quadratic paraboloid is the shape in between barrel and a cone. Therefore, it is not a barrel, it is also not a cone with a straight lines, bit thicker at the middle, but not like a barrel. Cone, now this is the quadratic paraboloid, this is the cubic paraboloid. Cone, straight. And the neeloid, if you can remember the trees in rainforest, most of the trees, the bottom area, they have buttresses. So, the neeloid shape is exactly like that, a tree with a buttress, the bottom part of the tree. It is more dent towards the inner part of the tree, and the form factor is 0.25 or 1/4. And the taper is the change of diameter along the tree stem. When you hear the term taper is 1 to 100, it means the diameter of the stem, if this is D1 and if this is 100 centimeter and if this is D2, D1 minus D2 equals 1 centimeter. This is what the taper 1 into 100 means. Taper 1 into 100, diameter changed by 1 centimeter after 100 centimeters along the stem. After next 100 centimeter, D3 minus D2 again becomes 1. And if it is 1 into 120, which means diameter changed by 1 centimeter at every 120 centimeter distance along the stem. Now, if you look at these two examples, I told you form and the taper are linked with the tree shape. The first one, same taper, diameter at this point D1, diameter at this point D2. For both logs, this is log 1, this is log 2. The diameter values of log 1 and log 2 at this specific distance is same. D1 of log 1 equals D1 of log 2, D2 of log 1 equals D2 of log 2. But the in between, the appearance is different. One log is more swollen, the other one looks more conical, more straight. Therefore, shape is different, therefore form is different, but the taper is the same. The second case, both logs, log 1 and log 2, both are same by the appearance, but the diameter values are different. First diameter, that is okay, D1 of log 1, D1 of log 2, they are same, but the second one, D2 of log 1 is not equal to D2 of log 2. Therefore, the second case, appearance is the same, but taper is different. What you want to realize is that there could be some trees with the same form, but different taper, and also some trees, they are different in taper, but similar by the appearance. And this is how we estimate the volume. There are different methods. Now, the first part we talk about the estimation of individual tree volume for research purposes. So, if you need so much accuracy in your estimations, there are three formulae built by three foresters or scientists sometimes back. The first one is the Smalian's formula, second one Huber's formula, third one Newton's formula. And when you compare, all the measurements are the same. We have the L, which is the length of the log, D1, diameter, all these D's are diameter values. All you need to measure is the diameter of the log and the length. Length is common for all the logs, but diameters, we have d1 and d2 here, dm here, again d1, dm and d2. When you compare, Huber's looks the easiest, Newton's looks the most difficult one to estimate. Now, how we estimate the volume of a log by using these equations? If this is the log, this is d1, diameter at the base, d2, diameter at the top, and then at the midsection, we have the middle diameter, and the length of the log is that. What we estimate is the volume. Now, for the Smalian's formula, you have to measure the bottom diameter, you have to measure the top diameter. Huber's formula, you have to measure the middle diameter only. Newton's becomes much more difficult because you need 3 diameters. For a log which is lying on the ground, which is very easy, but when it comes to a tree, that becomes much more difficult. And for scientific purposes, so if you need the volume mostly for very accurate estimations, we use one of these 3 formulae, and this example describes how we use Smalian's formula to estimate the volume. Now, imagine the tree is living on the ground standing, but hypothetically, but precisely, you have to divide the stem into pieces, right. Those lengths should not be equal because it is very difficult to get the equal distances, but most of the time we keep these section lengths equal as much as possible, but exact equal distances is not possible also in tree measurements. Now, we have divided the stem into sections. We have section 1, 2, 3 and 4. The 4th section, there is no top diameter. Therefore, we assume the 4th section as a cone. All 3 other sections, they are logs, they are wood pieces. Therefore, for the first log, first section, we have the bottom diameter squared, we have the top diameter measurement squared divided by 80,000 multiplied by pi value and the log length or the section length, and then it is done. We move to the second log. Now, the bottom diameter of the second section is the top diameter of the first section. Therefore, d2 becomes bottom diameter of the second section. d3 becomes the top diameter of the second section, log length or the section length and the pi value. We keep doing that until we complete all these sections, and the topmost section we estimate volume assuming that section as a cone, length, pi value, length. We get only the bottom diameter because there is no top diameter divided by 120,000. We measure the diameters in centimeters, we measure the lengths in meters. In that case, we estimate volume in cubic meters. If you want an easy method other than using this formulae, you can use already available volume functions. This is developed in Sri Lanka for Eucalyptus grandis or turpentine plantations in upcountry region. You have to measure the basal area, you have to measure the total height. You know that in forestry we cannot accurately measure the basal area. We measure the diameter and convert that into basal area. G equals 5d squared over 40,000. We measure diameter in centimeters, we estimate basal area in square meters. Therefore, we divide 5d squared by 40,000. By doing that, you have the basal area, so that your measurement 1 is diameter, measurement 2 is height, diameter convert to basal area multiplied by height, that gives you the volume in cubic meters. Now, you need to remember all these volume functions are species specific. For teak, you cannot use this specific equation, you have to have another equation. For another species like mahogany, you may need another equation, and for the same species, sometimes for good sites or good lands, you need one equation which could be different from the equations developed for Eucalyptus grandis growing in poor quality lands. And the other method, by the use, this is the easiest to use single tree volume table. This is a tabulated publication which is available in internet and also in hard copies. Even the forest department in Sri Lanka has some volume tables. These are also species specific. At the same time, they could be specific for the sites as well. For good sites, good growth, we have one table. Poor sites or poor growth trees, we have another table. This is one example. This volume table is available with the Forest Department Sri Lanka, which is for Pinus caribea or the Caribbean pine, low country pinus species. This estimates the volume up to 20 centimeter cutoff, which means it gives you the stem volume from the ground level to 20 centimeter, because the assumption is above this point there is no commercially available timber. Now, it has again two parameters. You have to measure the total height, you have to measure the diameter at breast height, dBH. Now, what happens, the assumption is very simple. For the trees of same dBH, you have different heights. For the trees of same height, you have different dBH. Now, in this example, if you measure a tree and if that pinus tree has a diameter of 25 centimeter and 16 meter in height, you have to locate these two, 25 centimeter diameter, 16 meter height. We have the volume up to this point, final cutoff point, 0.159 cubic meters. If there is another tree which is with diameter say 30, the height 21, we have the diameter 30, height 21, volume is 0.389. This is how we use a table. We call this two parameter volume table because you have to measure two parameters, parameter 1 dBH, parameter 2 total tree height. So, we discussed three methods of estimating individual tree volume. One, use of a formula, Huber's, Malians and Newtons. Two, use of a function. Three, use of a table. This table is called two parameter volume table because you have to measure diameter as one parameter and the total tree height as another parameter to estimate the volume. Next method, how we estimate the per hectare volume or volume per unit area. In that case, you have to have some samples, go to the forest, have a good observation, maybe you also need maps like Google Earth or paper maps, whatever it is, and then you demarcate adequate number of sample plots, same size. Each sample plot has so many individual trees. In that case, you have to measure those volumes, you have to estimate the volumes for each and every individual tree in the sample. You can use three discussed methods, either measurements like Huber's formula, Smalian's formula and Newton's formula, measurements required for one of these three formulae. The other one is to use a volume function, in our example Eucalyptus grandis, basal area and height, or single tree volume table, again you have to measure the dBH and the total height. And finally, you have to add all these volumes together, sum of volumes of all sample plots, and then it should be divided by area of the sample plot multiplied by total number of sample plots. All the samples, if you had 5.3 cubic meters of volume, your sample plot size is 0.02 hectare, it should be multiplied by total. Okay, now we discussed about measuring or estimating the individual tree volumes. When it comes to forest, we need the volume per hectare, what we call unit area volume, or per acre volume, or the volume of the trees in the entire forest. In that case, you have to have some sort of a sample plot, maybe demarcated by using random methods or systematic methods as we discussed earlier. So, the forest, you have to observe your forest by physically being in there, and also you can use the observations, you can use the paper maps or digital maps like Google Earth for your observations to identify the undulations and the growth differences to have a better sampling design, and then you demarcate your sample plots same size. Each sample plot has so many individual trees. You have to measure the required parameters to estimate the volume by the selected method. For example, if you use the measurements method, the formula method, you have to select one of three formulae, either Huber's or Smalian's or Newton's, and then you have to take the required measurements, or you can use a volume function. For example, Eucalyptus grandis, we discussed the volume function, volume equals 0.37 basal area into height, or the single tree volume table. Our example, you need dBH and height. Whatever the method, you estimate the individual tree volume separately, and then add all these values together, divide by the area of the sample plot, could be 0.02 hectare, could be 0.05 hectare, could be 0.04 hectare, whatever your sample size is, multiplied by total number of sample plots. So that if you had 10 samples, 0.02 multiplied by 10, and then the total volume of all the samples should be divided by this value, and then you can estimate the tree volume per unit area, in our example per hectare, inside the forest in cubic meters. That is all we need to discuss, and hope you enjoyed. Thank you so much.